My name is Mohammad Biroz Hassan, and I'm going to present a research paper today, which is titled "Attention is All You Need" by Ashish Vashwani et al. And it was published in 2017 in Neurips. And I'm going to present this paper for my artificial advanced artificial intelligence course. So So the motivation and significance was the traditionally dominant models. They used complex recurrence neural network (RNNs) and convolutional neural networks (CNNs), and they had sequential computing in them, and the sequential computing had long path constraints and inefficiencies, and the sequential computing, what it lacked was parallelization, and due to the lack of parallelization their training was very slow, and they consumed a lot of memory and GPUs in order to train. And the sequential operations for a layer, it required O into n time complexity for operations, where n is the sequence length, and the longer the sequence length, and the longer it will take time to train it, and the n must happen step by step, which made it too slow. And that was the pain point of the traditional state of the art models. And in order to reduce, or in order to overcome that, they came up with parallel computing techniques in some uh, in this paper. And the parallel computing, we create the sub problems, and then they ran parallel, and then it reduces that problem, and their goal was to reduce the sequential computing. So the challenges was the lack of parallelization, and this is the major dependency that discludes the parallelization within the training. And the next one is learning long range dependencies, and the path length challenge for RNN, and the growing path length challenge for the CNN. And as you can see in the table that the self-attention layer, it has a sequential operation of O into 1, and the maximum path is O into 1, which is a very less time complexity with reference to the recurrent and convolutional. As you can see that they has O into 1 and O into 1 for both the sequential operation as well as the maximum path length, and that would increase the time during their training, and representation dimensions of the uh, uh, embeddings, and for the kernel size of convolution as well. So their time complexity was bigger, and for the self attention, for the restricted, it is also less. So this was a major contribution that they did, and overcame those challenges in the attention is all you need in a transformer model. And their goal was to find a simpler network that could achieve higher superior quality, high blue score, or less training times. Yeah. So the key idea and contribution. So the key idea of the paper was a new model transformer. Fundamental design was to replace the recurrent and convolutional models entirely, and the model relies on entirely self-attention mechanism. And what it did was it maps the query q and the key value k and v for value pairs to the output of the model, and the self-attention o into 1 was constant number of operations. So the self-attention layer, what it did was it connects all position with a constant number of sequentially executed operations, which will create a parallelization in the model training. And in the output, there was an increased efficiency and less time during training compared to the RNNs or CNNs, and it was performed state of the art performance in the translation. And then if we move to the transformer architecture, then you can see that it included multiple things. First, word tokenization, then word embedding, then positional encoding, and it also had the multi-head attention technique, then masked multi-head attention, and feed forward, add and norm, and then output. So and on the right you can see the whole architecture of the transformer model, and we will explain that further, but first let me explain what word tokenization and word embedding mean. So word tokenization is like if when you separate a sentence into letters, words, and characters, and then you word embedding means you give the positional context to the tokens, and then you then put it into the input that into the model. So the transformer. So the transformer, it also had positional encoding, and that were added into the input embeddings of the model. And why they were added? Because the traditionally the recurrent and convolutional models, the recurrence, they had the context of the embedding, like where the words and characters were in a paragraph or in a sentence. But if you, and this model totally removed that. So in order to in order for the transformer to know that what is the point and where is the context of the sentence, so positional encodings were introduced, and they were put into the input and output embeddings. And then they have a scale dot product attention mechanism into the encoder, and then the multi-head attention is used, which projects the query and k-value pairs, and multiple heads were used, and in this specific model 12 heads were used. So what this masked head attention do? So this masked head attention in the decoder, as you can see, is that here what it did was it masked the uh, characters from the point where it is right now, so that the prediction is done correctly, and it only knows the letters which were behind that, so that the prediction of the second word adjacent to it is masked from it. So that was the main point of that. Then the encoder self attention was there, which comes from previous encoder layer as well. And then the decoder self attention, which I have explained, and which prevents the autoregressive property of the model. Then encoder decoder attention was there. So let me explain the attention mechanism, what it is. So the attention mechanism, we have scale dot product attention, and what it did was like the query and the keys were there, and then the values were then dot producted with the attention mechanism in a multi-head attention, and these heads can be multiple, but in this specific model they were 12 heads. And then the final output was concatenated, where head I was is equal to attention, and on top of that the dimensions were divided before dot product doing dot product with the values, so that it reduced, so that its value is reduced, and it is efficient. Then on top of that, softmax uh, function was applied for the computations to be efficient, and this was a very good approach to increase the efficiency. Then these are the results of the attention all you need transformer models, and as you can see, the model outperforms in blue score as well, and in the training cost as well, with respect to all state of the art models. And the results were very great, as you can see. And the transformer base model, it outperformed as well in the training cost, and transformer big model, it outperformed in the translation task with 228.4 blue score, and also 41.0 score of blue score, which is very good with respect to the training cost that it took. And now coming to discussion and summary, these models are more parallelizable, and they required significantly less amount of time to train. So the large model achieved the best result after training for 3.5 days on 8 NVIDIA L100 GPUs, which is very small fraction of the previous score of the state-of-the-art previous models. So now the transformer successfully generated English constituency parsing and achieving 92.7 F1 score in a semi-supervised setting, which was great at that time. And the model, it performed a very good translation task in of English to German, the transformer big model, and it achieved the, as we mentioned as well, it achieved the state of the art blue score of 28.4, which was great. And the self attention, it provides the side benefit of interpretability, which was great at that time as well. And now, if we move to the strengths and weaknesses of the paper, so the strengths of the paper were that it has superior parallelization and lower training cost with respect to all the previous state of the art or benchmark models like RNN or CNN, and it eliminates the sequential bottlenecks and the self attention mechanism. It enables full sequence parallelization and achieve results with 75% less training cost, state of the art results. And the second strength of the paper was the constant path length for long range sequence dependencies. So it has only the self attention, it reduced the input output path length to O into 1 number of operations, and it outperforms RNN time complexity and CNNs on the same hand. And then the state of the art quality and strong generalization, as we mentioned as well, that it performed on very good English to German and English to French translation with benchmark capabilities. And now we discuss the weaknesses of the paper. So I have found that the weakness of one weakness of the paper was quadratic complexity for long sequences. So in the attention mechanism, the self attention scales as O n raised to power 2 with sequence length. So what it did was it was faster than RNNs when only the sequence length was less than the model dimension. So when the model dimension was greater, so it was the time complexity increased. So this was one weakness that I found. And the other was numerical instability during requiring, it required scalability. So dot product attention, it needs a scaling factor for one over the dimension to prevent the softmax saturation. So the saturation was happened during this time. So large dot product caused a tiny gradients, the unstable learning. So this was the weakness of the paper. So improved adjustments, so implement and evaluate the restricted attention for long sequences so that this time complexity for the quadratic scale product doesn't happen, which we mentioned earlier. So this was all from my side. Thank you for your attention.